Hi everyone. So this is my first video showing you how to do I think the third extension question which I set in class the other day. But yeah, these ones, the BMO questions. I think they're the hardest. I really do. I think they're harder than STEP and Matt and Tamua. I mean, the thing is, the content isn't harder. They won't ever ask you to integrate or differentiate. They won't ever ask you about trigonometry, it seems to me, or very rarely anyway. In other words, the kind of mathematics that's in the questions is only, can we put in inverted commas, GCSE maths? But they're so difficult. They really are. The exam, by the way, the test or the challenge, whatever you want to call it, is sat by, I believe I'm right in saying, about 1,000 students in the country every year. And then round two, and round two, whenever I've looked at any of the questions on round two, I'll be perfectly honest, I'm out of my depth, I really am. But round two is sat by the top 100 students in the whole country. So I think I just have to accept here that the top 100 students in the UK every year are definitely smarter than me. Yeah, it's really very challenging, but that's why I like doing it as well. I've always liked, challenges. It's always great fun, isn't it, maths, if you've done something which you know is really quite a difficult question. And so, I do want to encourage you with these as well. I know I've just spent, the last 2 minutes saying how difficult it is, but we can do this. That's the way I like to, I like to encourage people. We can do this. And honestly, I don't consider myself like incredibly gifted in maths at all. I really don't. And if I can get some of these right, you can do it too. You really can. So, okay, how did I do this question? Well, let's have a look at it first. Find, showing your method, a six-digit integer such that it's a square number and the number formed by the last three digits of n is exactly one greater than the number formed by the first three digits of n. So an example is 123, 124, except it's not square. Yeah, so it's not a good example. I mean, they don't want to give away the answers in the question. Now I'm going to answer this question. I'm going to show you that my method can produce other results which have this property as well. So I'm going to give a couple of answers and kind of show off a bit. But okay, so what are we looking for? Well, we're looking for n so that it's a square. So we've got n is p squared. And we know that n must have six digits. Yeah. And I suppose when I say n is p squared, I should say p is an integer, therefore, or should we say p is a natural number? Yeah. P is basically a whole number. That's what I'm saying there. P has to be a whole number, or n's not going to be a whole number, and n is obviously a whole number. That's why they've called it m. Now, n also has six digits. And also, how could we write this? Coming up with a way of writing this is important. And it really is a very critical step that you need to take to getting this question right. Well, the way I modelled it was like this. I said p squared equals 1000m plus m plus 1. Now, let's convince ourselves that that is always going to form a number like this. Well, for example, if m was 123, yeah, then to make 123,124, I would do 1000m, that would be 123,000, plus m plus 1. And so that would add the 124 in the end. So that will always result, regardless of the value of m, that will always result in a number which has this property, provided, of course, m is bigger than 100. And this is going to bring us into the next thing I want to say about like the restrictions we can place on the value of p and the value of m, which does actually really help us in this question. So it's important to note that this only works for six-digit numbers if, well, let's talk about the restrictions on p first. Maybe it's more natural to talk about the restrictions on p first. Clearly, we want n to have six digits. So we want p squared to be trapped between 100,000 and then up to, but not including, a million. And so that ensures that p squared and therefore n has six digits. Yeah. Now, when I first did this question, I square rooted it, and I had to estimate the square root of 100,000. I didn't have to estimate the square root of a million because the square root of a million is just 1,000. But when I first estimated it, I estimated it to be 320. I think it is in fact 316. And it's or 315 point something. I can't remember now. I haven't got my calculator. But if we say that p has to be I think it is actually strictly greater than 316 because of the value on the calculator. You can check it on a calculator, but I want to point out that we do not need incredibly good accuracy here. I'm just trying to give myself an idea of the values which P is trapped between. That's all I'm trying to do. Yeah, it might help me in a little bit. Now, what's even more important really is the restrictions on M. Now, M has to be trapped between 100 and 1,000. Yeah. Now, why is that? Well, because otherwise we're not going to end up with a 6-digit number. You know, if M is 123, you're going to get 123, 124. But if M was something like 1,000, well, you're doing 1,000 times 1,000 then, so you've already got a million, and you're breaking the restriction on P squared. Yeah, and therefore you no longer have a 6-digit integer. So all these things were just kind of kicking around in my head. Now, the fun bit, though, by far, the fun bit is if we can call this star, it's rearranging star, because what do they normally ask you in these questions? What tricks normally often come up? Well, the kind of tricks which often come up are difference of two squares, for example. And I think I've got an opportunity to do difference of two squares there. So I'm just going to move this. I'm just going to move this question down a little bit. I think we've got enough of the question. We know what we've got to do now. I'm going to rearrange this into p squared minus 1 equals 1001m. Yeah, let's call that star. Now, a bit like in the step question, which we did, where we factorized it, even though it wasn't equal to 0, I'm going to do the same thing here. I'm going to write this as p plus 1, p minus 1 equals. Now, factors 1001. You can look, you can check it's not divisible by 2, obviously it's odd. It's not divisible by 3 because the digits don't sum to 3. Always look for that trick. It's not divisible by 5. Obviously, I don't have to check 4 because we're only looking for prime factors. It's obviously not divisible by 5, so you might want to try 7 then. And you do need, I know some of you are freaking out by the fact that these things are all done without calculators nowadays, well, and always were actually. Nowadays, these exams are always no calculator, and they freaked you out a bit with the the arithmetic. Let's go over this then. 7s into 10 go once, remainder 3. 7s into 30 go 4 times, remainder 2. 7s into 21 go 3 times. Yep, that's right. You've got to be clever to do long division or short division in primary school. So 7 times 143. Now, I'm pretty sure 143 is prime, actually, for similar reasons to what I was just saying. It's clearly not divisible by 3 or 9. It's clearly not divisible by 5. It's then you've got some prime numbers which are slightly larger, which you might want to check, maybe 17, 13, 19 even. Remember, you've only got to go up to the square root, when you're checking for factors, because factors always come in pairs, and the square root of this is about, actually we've only got to go up to 11, haven't we? And so as it's not divisible by 11, I can see I've actually expressed it as a product of its prime factors. But anyway, I just wanted to do that really because the next bit is going to be the clever bit. Okay, what is the clever bit? Well, as you can see, we've got 7 times 143 times m. Now, m itself may not be prime, it might be composite, yeah? So you might be able to factorize that bit further. But remember, I'm just looking for values of p and m that satisfy this condition. Because if it satisfies this condition and it satisfies the conditions which I'd written down here, yeah? If it satisfies all those conditions and the star equation, if it satisfies all of those, then we've done it. We just have to find a number. They're asking us to find a number with that property. Yeah. So let's try and do it. Well, clearly p plus 1 is 2 more than p minus 1. Yeah. And one of these, the way I did it was I kind of thought, well, one of these, maybe it's this one, maybe it's this one. One of these is going to be a multiple of 143. Yeah. And the other one is going to be a multiple of 7. Yeah. So I'm thinking M is probably composite, yeah, as in like it might be prime, I suppose, but I'm going to have it probably as composite, and so one of its factors is going to go with 143 and match to. Maybe I should try matching these up because this is probably the easiest way to understand it. One of my factors will go with a p minus 1, and one of them will go with a p plus 1. So what I mean to say is, if I've got like one of them as a p minus 1, like 143 times 2 or something as a p minus 1, well then 7 times something else will be the p plus 1. I was supposed to do that in red, sorry, I've messed that up. Anyway, let's keep going. So what I need to do essentially is I'm going to look at 143, oh, I've got the wrong pen, sorry. I'm going to look at 143 times 1, for example, yeah, and it equals 143. And then I'm going to check, like, I'm going to say maybe that 143 is the p minus 1, and therefore the p plus 1 would be 145, and then I want that to be divisible by 7. Now, I hope you can see pretty quickly that 145 isn't divisible by 7. So my lame attempt has failed, if you like. But I don't have to do it with times 1. I can just keep checking numbers to find multiples of 143. And I want 2 more or 2 less than 143 to be a multiple of 7. That's what I'm looking for. Now, you could try timesing it by 2. You get 286. You can check 284 and you can check 288. And the reason we're checking 2 below and 2 above is because we're saying, well, maybe the 286 is this one, in which case I need to look at 288 and see if it's divisible by 7. As it happens, it isn't once again. You can see that pretty quickly. Or maybe the 286 is the p plus 1, and I need to look 2 below to see if 284 is divisible by 7. And sadly, it's not again. Well, you might start losing heart with this method at that point, but once you just go one more step in that direction, 143 times 3, you get 429, yeah? Now, if you check 431, that's not divisible by 7, but if you look at 427, you should be able to see pretty quick that this is divisible by 7, because it goes 61 times. So here's my strategy, and I've cracked the question at this point. I really have, because what I can allow for is that 143 times by 3, and this m is going to consist of 3 times something else, and in fact it's going to be 3 times 61. And so what I'm saying here is 143 times 3 can be the p plus 1, and the 7 times 61 can be the p minus 1. And therefore I've found the value of m and I've found the value of p, which satisfies that equation. And you'll see as well that I'm satisfying those conditions which are oh so important in this question. So what have I really done? So I'm going to write that out again. I'm going to say, okay, by inspection, if you like, this is how I'm going to write up my solution in the paper. By inspection, 3 times 143 is 429. And 427 is divisible by 3. By 7. And it equals 61. Yeah? And thus, what I'm actually doing is I'm setting p plus 1 to equal 429. Yeah? And p minus 1 to equal 427. And therefore, I'm going to have my m equal to 3 times 61. I've therefore got everything that I need to find my number now, because I've already got the formula which does it, yeah? And it's probably easier to use the 1000m plus m plus 1. I could find p here, because p is clearly 428, and just square 428, but that would leave me with some long multiplication at the end, and you know how bad I am at arithmetic. Okay, so let's just write down now our final answer. So p squared, if you remember, is 1000m plus m plus 1. And so that equals, as 3 times 61 is 183, I could have 1,000 times 183, well, that's 183,000, and then 183 plus 1, well, that's 184, yeah? Now, that's p squared. Now, what is that the square of? Well, without even working it out, I can say that must be 428 squared, yeah? And you can check it on a calculator. I'm fairly sure it's correct, but 428 squared equals 183,184, and I've cracked the question. Now, just to show you that the method I've used actually will find others as well if you actually pursued it forwards, because 4 times 143 is 572, yeah? And if you check 574, 574 is divisible by 7. Yeah, let me not write it so bunched up. 574 is divisible by 7. I think it goes, I can't remember. 8, remainder 1, 2, so it goes 82 times. And therefore, this time we'd have p plus 1, p minus 1. It's nice to write them down underneath, equals 7 times 143 times m. Well, m is therefore going to be 4 times 82. Yeah, your p plus 1 is essentially going to be the 574, and your p minus 1 is going to be the 572, which matches up with the 4 times 143 there, and the p plus 1 of 574 is the 7 times 182 here. Okay, and does it work? Well, let's have a look. I think it gives me, now I've got, what is 4 times 82? 328, yeah? So m is 328, and therefore p squared, remember it's 1000m plus m plus 1, and so it equals 328,329. And my p, by the way, is going to be 573. Now, certainly the last digit checks out, but you can check it on a calculator. Is 573 squared that? I'm hoping it is, because my method is telling you it is. But yeah, check it on a calculator by all means. I hope you enjoyed that. Really, what was the trick there? Difference of two squares. What was the difficulty of the question? Extreme, I would describe it as. I'm sure other fantastic mathematicians would not feel like that, but I find it extremely difficult. But it's good fun. I actually did this question when I remember doing it when my first child was born in the hospital, because I just brought some maths with me, because you have to wait for hours for some births can take hours and hours and hours. So I brought this one along and was quite pleased how it all worked out, actually, and it took my mind off things. So there we go. Maths is a great thing to have in your pocket if you've ever got to wait around for hours and hours with no news. I suggest you give it a try. Okay, all the best, and thank you for listening. And yeah, I hope that was quite good fun. I hope you learnt something. Okay, bye bye.